We're going to look at the incident energy calculations here in a little bit for low voltage, and then the arc flash boundary. And then a little bit later on, we're going to move into the medium voltage problems. And with medium voltage, you might be thinking, oh gosh, that's right, we have to do two calculations. With the two calculations, the way I'm going to structure that is I'll be solving one of them. That'll be the illustration. So I'll solve for the lower voltage, like perhaps 2700 volts. And then you can take a look at the higher voltage, 14.3, and then we'll perform the interpolation together. And the 30,000 amp case, I tried to make this identical to the case that I had for my 2002 class, as I had mentioned. We had 30,000 amps of bolted short circuit current, 30 kA. The gap that was used in the original problem was 32 millimeters because it's switchgear. The duration that I had in the original problem from my 2002 class was 30 cycles, 500 milliseconds. Now, those of you on using 50 hertz systems, because we've got a lot of people from around the world here, forget about cycles. The actual input value is milliseconds. So as long as you're inputting milliseconds, everything works out. The enclosure size, the default enclosure size from back in 2002 for switchgear was 20 by 20. So we're going to stick with that. And the nice thing about that for this problem is using the 20 by 20 enclosure size, that's the default value. If you don't make any correction for different heights and widths and so forth, the default's 20 by 20. So all that means for us is we don't have to address the correction factor for the enclosure size. The IEEE adjustments only go down to 20 by 20. And what you're going to see, I'm going to answer a lot of this when we get into the calculations, but when a size is less than 20 by 20, you just lock in at the 20 by 20 value. The only time when going smaller is going to require an adjustment is if it's shallow. And if it's shallow, because of the depth, the energy actually decreases. Again, because the electrodes are closer to the front. So I think you're going to see we're going to answer some of these questions as we go a little deeper and actually get into the calculations and the equations. For this video that I have right here, this is, you can see the enclosure is shallow. It's about that deep, so it's less than 8 inches. And it's 3 flat electrodes, and then you can see the shorting wire down at the bottom. So go ahead and cue up the video and take a look at how the energy kind of diffuses out. 3, 2, 1. So with that one, because of the depth, the energy kind of shot out, I use the term diffused, less dense, as the energy is closer to the front.